Hello, everybody. Thank you for coming. We have a distinguished guest here today, Ayman Fayed from Iowa State University. He received his Bachelor of Science from the Cairo University in 1998 and then joined Ohio State University and received his master's and PhD in 2000 and 2004. In 2000, he joined Texas Instruments and held a number of roles, working on transceivers for USB and FireWire, data converters for mobile communications, and power management for mixed signal system on a chip. Afterwards, he joined Iowa State University, that was in 2009, and founded the Power Management Research Laboratory. His primary areas of research include embedded power conversion for RF and mixed signal system on a chip, energy harvesting applications, data converters, and high-speed wireline transceivers. So, welcome on.
Thank you very much for the introduction, and thanks everyone for coming in today. Today I'll be talking about a specific topic of interest in power converters, Spur-Free switching power converters specifically for analog and RF loads. The outline of my talk today, I'm just going to spend like one slide talking about my personal background and the research group that we have at Iowa State. And then I will talk to you guys about power management, what is it, and why is it something that is becoming popular these days. And then I will talk about specifically the switching noise problem in power converters and the different ways that we mitigate this problem and a proposed approach that we came up with to handle that. And then I will talk towards the end, if there is some time still left, I will talk about power management and formal education. It's a topic of interest to me, so I'll talk a little bit about what can be done to improve the education process of power management in electrical engineering. So as I was introduced, my master's and PhD is from the Ohio State University. I spent about 9 years at TI working on different product lines from high-speed wireline and data converters and power. We currently have 6 PhD students and 2 master's students in my group working on different projects, and we graduated 1 PhD student at Broadcom and 1 master's student at TI right now in the past 4 years. The research interest that we have in our group, we basically are very interested in building what we call smart on-chip micro-power grids for highly integrated RF SoCs and analog and mixed signal SoCs. We also do power modulators for RF applications, power amplifiers for audio applications, energy harvesting, and also power conversion in emerging technologies like GaN and similar technologies. So let me move into power management. What exactly is power management? What you realize after leaving industry, when you say power management in industry, people know what you're talking about. But when you go to outside of that and you say that you do power management, people have different ideas of what power management really is. So I thought I would spend a couple of minutes talking to you guys about the different possibilities and how this is not what I do. But if you talk to a system designer, power management to them is task-oriented, basically what should be turned on and what should be turned off for a specific task to kind of your laptop, different profiles, for example. That's what happens when you say I do power management. If you're a systems guy, a digital designer, it's all about dynamic voltage scaling. How do I move my power supply up and down depending on what kind of performance I'm looking for? That's also considered power management. You talk to a chip architect, it's about power delivery. How do I deliver power from the pins to different places on the chip without too much IR drops and things like that? But if you talk to somebody like me in the analog domain, it's not really about how you manage power or conserve it or deliver it. It's really about how you convert it and regulate it. How do I generate from an unregulated energy source a well-regulated power supply? So it's essentially power supply design. That's what we mean by power management today. Okay, why is this issue becoming very popular and very important these days? There are several reasons. I'm going to briefly just describe to you guys why this is the case, but if you really look at battery life, it's becoming a very critical issue for us. If you look at the iPad 3, they had to use, I think, 30% bigger battery or something just to be able to keep the same functionality while maintaining the same battery life. And battery technology has been stagnant. It doesn't really move as quickly as the advancement that we make in the electronics industry, and you still want to jam in a lot more functionality. For the past 15 years, that has been addressed on the load side. So people try to design loads with low power consumption, led to technology scaling and things like that, but that's really yielding diminishing returns. So we have to go back and revisit how we are delivering power from the energy source to the load in order for us to be able to improve battery life any further. So that's one big reason why power conversion is becoming very popular. And also there are different methods now that we are considering to power our systems to reduce the total power consumption, like adaptive powering. And in these methods, you're actually required to implement a large number of independent power supplies. And that's always a problem in our systems, because traditionally, when you are trying to implement efficient power supplies, they cost you passive components, a lot of silicon area. It's just a very costly and very expensive thing to have in the system, to have one power supply, let alone having 20 or 30 or 40. So that's another reason why this area is becoming very important. And of course, if you look at most of our SoCs today, everybody's able to integrate their stuff inside minimal package pins and components, except you, the power management guy. You're the only one who's taking most of everything. So it's becoming really a bottleneck in terms of how we implement our devices today. Thermal efficiency is also a major issue. Sometimes you have to be efficient, not for battery life purposes, but you have to be efficient because you can't get rid of the heat otherwise. So that's another reason why we have to consider that. And the specific topic of today, that efficiency versus noise, these are two contradictory things. If you want to do something that is low noise, that means you have to be inefficient and vice versa. So we try to work on different ways of maintaining efficiency while maintaining also low noise performance. So that's why power management is a big deal today. So let's talk a little bit about the topic of today, the switching noise problem. And since some of you may not be very familiar with what power supplies look like, so I'm going to spend a couple of slides just discussing the two main types of power supplies that we use. There is what we call a linear regulator that you see here on the right, and a switching regulator to the left. And basically the basic idea, a linear regulator, what you do is that you insert what we call a power transistor and you adjust the resistance of that power transistor so that at the desired output and load current, you drop the difference across that power FET so that you can achieve regulation this way. A switching converter, it's a little bit different concept. You basically actually switch, or you chop the input voltage in a certain way so that the DC component of that chopped voltage is exactly equal to the output power supply that you're interested in getting. And you filter that chopped signal by an LC tanks to get a smooth and nice DC output from there. Main differences that I would like you to be aware of, that linear regulators, they're not very flexible. They can only step down the voltage. You can't really step up the voltage. And they're known to be very inefficient in terms of energy, but they are very low noise and relatively small cost and size overhead. We can really implement those linear regulators on the chip. We don't even have to use an external cap anymore. So very cheap to implement, really. Switching regulators, on the other hand, you can step up, you can step down, or both. They're known to be very efficient, but they're very noisy. We'll see why. And they actually cost you a lot of area and component overhead to be able to implement them. Now, for people who are not familiar with the concept of efficiency, I like to use an example from civil engineering, and people relate to that example to see really how dumb a linear regulator is in terms of efficiency. But you can imagine the following scenario. Imagine that you have a civil engineer that is faced with the problem of trying to build a pipe of water. He's trying to regulate water, and he has a pipe that has this kind of funny shape, a wide input and a narrow output that represent a higher voltage and a lower voltage. And he's trying to keep that water flow regulated. So how does he solve that problem? He pokes a hole into this pipe and dumps the extra water to the ground. So what would you think of a civil engineer who would do that? It's such a waste, right? Because you're just getting rid of that extra water. That's exactly what a linear regulator does. So from an efficiency point of view, you can see how bad that is when you do something like that. And even this is the case, we're using linear regulators everywhere in our chips. In a switching regulator scenario, things are different. Instead, you actually install a gate, right? And then kind of like what you do in a water dam, and you turn on that gate periodically just enough so that you pass the flow of water that you need in your system. And these two examples tell you immediately the trade-off. If you're passing water in bursts like that, that means that the flow that you're getting on average is what you want, but it will be what? Very noisy flow. right? Because you're passing it in burst. While in a linear regulator case, you are having a very smooth, low noise flow of water. So that's just an example to show you that. Now, the efficiency, lack of efficiency in linear regulators is not a trivial matter. And I'll use an example here of an incident that happened with me. A colleague of mine, he was designing a data converter, and he was trying to design it with very low voltage so that you save a lot of power. And he was designing something to operate from 1 volt, and then I was the power guy, so he comes to me to talk about powering the ADC. And I told him, why are you doing that? He said, well, I want to save a lot of power in that data converter. I told him, but our system does not have except a 1.8 volt supply, so where do you expect to get the 1 volt supply for your data converter? And the immediate answer was, oh, we'll just use an LDO from 1.8 to 1 volt. And then my answer was, well, you might as well just design your data converter directly from the 1.8 volt supply because you're saving nothing by doing that. Why? Because whatever you're saving, you're burning across the LDO. So that efficiency question is something that people often miss, and it's very critical. If you don't know what you're doing, then you might end up actually increasing power instead of reducing power. Okay? So now that takes us to, if we don't like to use linear regulators and we'd like to use switching regulators, so what exactly is this whole thing associated with switching noise? Well, you can simplify the switching regulator system, no matter how you're controlling that or whatever. At the end of the day, you're ending up in a steady state scenario that you're creating what we call a switching voltage between the input voltage you're getting the energy from and ground, and you're creating that with a certain duty cycle so that the average of this switching signal is equal to the DC component that you're interested in. And you can think of the LC tank as a low-pass filter to get rid of all the switching noise or all the harmonics, and you extract the DC component of that signal. Now, we all know from signal processing what the spectrum of such a switching signal is. It will look like, a series of harmonics that have a sinc function as the envelope, right? So it will have the fundamental and all the harmonics. And then you would have the low-pass filter from the LC tank, but unfortunately, once you take into account all the parasitics associated with these components, you end up injecting zeros in the transfer function of that low-pass filter. And instead of filtering these harmonics out, you actually end up saturating, and when you look at the spectrum of the converter, you see harmonics all the way to very high frequency with significant magnitude that the LC tank is unable to actually get rid of. And that basically disturbs the performance of any load that is sensitive to these spurs, we call them, or tones in the system. So that's where that switching noise is coming from. Just to show you an actual measured result, this is basically an off-the-shelf converter that we brought in to do some testing, and you can clearly see this is with PWM control, meaning that the switching frequency is constant. And you can clearly see that the fundamental is very large, but when you look at the harmonics all the way to 30 megahertz, you still have significant spurs that you can see in your system that can really disrupt your performance. Okay, so what exactly is the impact of these spurs in your system? I'm going to just give you a quick example of how this can be bad for your system. And the first example will be associated with direct powering. So let's say that I take an RF power amplifier, a GSM power amplifier, and directly power it from a switching regulator or a buck converter. Well, once you do that, what happens is that the spurs from the power supply will mix with the RF carrier, and then you end up at the output of the PA. Instead of seeing your carrier only, which is the middle one, you see these two little spurs to the right and the left due to the mixing at a frequency offset that is exactly equal to the switching frequency of your regulator, and you end up makes it impossible for you to pass the spectral mask of the power amplifier with these two little spurs poking out like that. That's an example of how this can be problematic in an RF system due to direct powering. But direct powering is not the only thing that you deal with. Oftentimes, the mere existence of the regulator or the switching regulator in your system is problematic, even if you're not using it to power your load. For instance, let's say in load power DSPs, that's very popular. You would have a switching regulator operating from your 1.8 volt supply and generating 1.2 volt for your digital circuitry, but you have other circuits in the systems, like a data converter that still needs to be run from 1.8. But the problem, because you don't have enough package pins, you cannot have a dedicated 1.8 volt supply for your data converter. So you have to share that supply with the buck converter itself. Well, guess what? Everything this these two power FET switch, they create a pattern on the 1.8 volt rail and ground due to the parasitics associated with the package pin and so forth. That will actually interfere with the operation of your ADC. And then you look at the output spectrum of the data converter, you can see the spurs coming from your buck regulator showing up at the output, even though this guy is not powered by the buck converter, it's just sharing the rails with it. So its existence in the system is a problem by itself. Well, but that's, you can say, okay, let's not share that stuff and get rid of that problem. Well, you're sharing the substrate, and that's a problem. If you look at these power converters, we typically have to insert what we call dead time, where both transistors are never turned on at the same time so that you don't create a short circuit. And during that time, your inductor is full of current. It has to find a path to discharge that current. Where does it get it from? From the body diode of the low side power transistor, which takes it from the substrate. So that means that you're debiasing. You're moving your substrate up and down every time this thing is switching, and that substrate is where everything is actually implemented on it. So you can see that this can also cause a problem for your noise-sensitive circuitry just because this regulator exists in the system. Okay, so how do people deal with this issue? There are two fundamental ways that people consider. There is what I call time domain approaches and frequency domain approaches. One I consider a smart approach, and one I don't consider very smart, and you'll see why. But this figure is a summary here of the different ways that people deal with that. Some people say, forget it. I'm just going to use a linear regulator and deal with the fact that this is very inefficient. So that's not very good for obvious reasons. Some people say, well, let's use a switching converter, but maybe follow that with some sort of passive filtering, maybe a linear regulator, and hope that the linear regulator will filter this noise out. So you're cascading two regulators to get rid of it. Well, it doesn't work very well anymore, and we'll see why. Some people use active ripple cancellation. So they look at another name for switching noise is ripple, because it appears at the output supply as ripple. So we look at it from a time domain, and we say, okay, let's just make this ripple a lot smaller, and that will solve the problem. There are interleaved DC to DC converters. We'll talk about that. There is now frequency hopping is something also that people do, and we're kind of exploring that. And there is also sigma delta control. So both the frequency hopping and sigma delta control is to manipulate the spectrum. So let's go very quickly over these different things. LDOs, they don't work very well anymore, because what happens is, if you look at most of the LDOs that we implement, you look at the power supply rejection profile from these LDOs, and you can actually see that by the time you get to the 3 megahertz or the frequencies that are commonly used in switching regulators, these things hardly have any power supply rejection. So what happens is that this noise goes straight through the LDO and shows up at the output, unless you use maybe an external capacitor for this LDO to try to improve its power supply rejection. But again, it goes back to having to use a capacitor there, which is not something that is desired in our system. So it's not very effective anymore. Active ripple cancellation looks at the problem from a time domain point of view. It says, why do I have ripple at the output? Well, because I have ripple current into the inductor due to switching. But if I observe that ripple current, and maybe add in parallel to that something that is complementary, then they can cancel each other out, and I have a smooth load current going into the output. So that's the idea of active ripple cancellation. It's a time domain idea. And certainly you could do that, but there are some issues. First of all, this amplifier that you have to use is linear, so you're actually wasting a lot of energy doing that. It has to be pretty fast. It has to be at least as fast as the switching frequency of the regulator itself, which means that you have to use a lot of quiescent current to do that. So in general, it is just, from an efficiency point of view, you actually lose a lot by doing active ripple cancellation, especially at light load kind of conditions. Another technique that people also explore is to do basically interleaved converter. And the idea there is to say, active ripple cancellation uses those active circuitry to cancel out the ripple, but can I actually cancel out the ripple current into the inductor by another inductor, which is an efficient way to do that? And sure, you can actually build different phases of the same converter, and you add them up in a way so that the ripple current from all the inductors will add destructively. And that can actually reduce the ripple quite a bit by doing that. But then, guess what? People are unhappy with that one inductor to generate a single supply. So imagine if you're asking them to have 3 or 4 different phases of that inductor. So it's not a very cost-effective method of dealing with this issue. Now, these two specific examples that I gave were dealing with the noise from a time domain point of view. Let's look at it in time domain, try to reduce that as much as possible. But if you're doing analog design or RF design, you know that looking at noise from a time domain perspective is not really the right way to look at it. You can probably tolerate a lot of noise if it happened to be allocated in the right frequency or has the right shape for you, right? So you really have to look at it from a frequency domain point of view rather than a time domain point of view. And one of the techniques that is out there that looks at it this way is using a sigma delta control to control the buck converter or the switching converter rather than traditional PWM. And in these types of control, as you know what sigma delta is a 1-bit kind of sigma delta. And what that does, it injects a lot of random quantization noise in the system. And the hope is that when you overwhelm the system with this random quantization noise, then you will be able to spread down this spurious noise that is coming from the switching regulator itself. So we're kind of trying to randomize in a certain way using a sigma delta how the converter is actually switching. And sure enough, that result in significant reduction in Spurs. For example, from this paper, this is just something that shows you a regular PWM control, which is the dotted curve, versus a sigma delta controlled converter, which is the solid curve. And you can see there is significant reduction in the Spurs, but they do still exist. But notice the following, that you have a very large increase in the random noise floor. So the random noise floor is going up quite significantly, which can be problematic for many other types of loads. And you can see that there are subharmonics that started to appear. Why? Because once you disturb the switching of the converter, you're disturbing its steady state. And every time that happens, you create large transients at the output that happen at the same rate of the data converter. And then this actually gets folded back, and you start seeing these subharmonics. So you may be fixing the problem in one frequency range, but you're creating problems in other frequency range. So that's a disadvantage of using that sigma delta. Another technique that people are importing from communication theory is actually frequency hopping. And it started a couple of years ago that people started to work on that, including ourselves. And just to explain the idea of frequency hopping, let me spend a minute here explaining something real quick. We're creating a switching node right before the inductor with a single switching frequency. So people thought, okay, what happens if I keep randomly hopping between two frequencies, let's say, F1 and F2? What happens to the spectrum when you do that? And, well, you can look at it simply as if, one frequency is there half the time statistically, the other frequency is half the time there statistically. So if I look at the spectrum, I will see two Spurs at F1 and F2, but they will have a smaller magnitude because they're there only half the time. In fact, exactly 6 dB smaller magnitude. That's an intuitive way to look at it. But mathematical way to look at it, you can always, take your original signal that has multiple frequencies. You can actually take that and divide it. And this is just mathematical manipulation. It is not real. But you can imagine that you have what we call a baseband signal that it oscillates between 1 and 0, 1 when you're passing F1 and 0 when you're passing F2. And you create a complementary signal that looks exactly like this, but complementary. And you create two continuous clocks at F1 and F2, and then you can argue that this signal is actually equal to the product of P1 multiplied by the blue frequency, and then P2 multiplied by the red frequency. That's how people analyze frequency shift keying in communication, for example. But once you do that, then you kind of understand what's going on, because from a frequency domain point of view, you can analyze this by taking the spectrum of this signal, P1, and simply modulate it by a carrier. So it becomes like AM modulation, and we all know what happens. You take the spectrum of this guy, and you essentially shift it or up-convert it to the frequency F1. But when I look at the spectrum of this signal, what do I see? I see a sinc function, because it's just like a square wave, a random digital sequence. But I see a DC component of this signal that is exactly equal to half, because statistically half the time it's 1 and half the time it's 0. So I end up with a DC spur plus the sinc function. Then you modulate it by the frequency. So you end up with two spurs that are exactly 6 dB lower than what it would have been with a single switching frequency. And now if you increase the number of frequencies that you use, then you can actually reduce the spurs even further. So that's a basic idea of traditional frequency hopping. And some people worked on that in the past. This is an example of people who did exactly that, but they used 8 frequencies. And you can see the results at the output of the power amplifier. You can see the carrier. You can see the 2 big spurs when you don't do frequency hopping. You enable frequency hopping, you end up with 8 smaller spurs. It's about 10 dB lower in the level of spurs than in a single frequency case. So you can get improvement, but you can clearly see that spurs still exist, they still mix, and then it is not as effective in actually solving the problem. And there are issues associated with frequency hopping too in buck converters. They actually do generate subharmonics too, because every time you actually switch, because you're hopping at a constant hopping rate, you don't really have control on where hopping exactly happens. So you might be disturbing the switching duty cycle of the converter every time you change the frequency, and that will manifest itself as these big glitches every time that you actually change the frequency, and it will show up as lots of subharmonics at low frequency. So that's a major problem with frequency hopping. So what do? We looked into this problem a little bit, and then we actually decided a couple of things. We decided to continue to adopt random frequency hopping so that we avoid injecting extra noise in the system. The sigma delta example that I showed you, the reason the noise floor goes up quite dramatically like that is because I'm injecting a lot of quantization in the noise in the system in the hope of spreading this noise. So it's kind of like I'm making the random noise floor so bad so that I can kind of hide the spurs there, right? That's the basic idea, which is not a very good thing to do because you don't want to add more noise into your system. But then what we did is that we adopted a variable hopping rate. So we decided to use a variable hopping rate instead of the traditional constant hopping rate. And that turned out to have a lot of advantages, as we will see in a little bit. That variable hopping rate will minimize any disturbance during hopping, meaning that you're no longer going to have those glitches showing up anymore. We'll be able to get maximum spur reduction with minimum noise floor peaking. But then the key is that we added a factor called random phase chopping, that's what we called it, that will not only reduce the spurs as traditional frequency hopping, but will fully eliminate them. So let's see how that works. This is how the architecture is. And if you look at the design of the converter itself, it's a very simple design, really, nothing fancy in terms of the converter. But most of our work was actually the way you generate the ramp. So let's focus on that a little bit. So if you look at our ramp signal generator, which determines how the converter is switching, what we're doing here is that we have a bunch of current sources on the top that we actually use. And these current sources here are essentially, one of them at a time is used to charge up a ramp capacitor. And then we have a magnitude detector that observes this ramp signal. And then once it reaches a preset magnitude, it will actually send a signal that will trigger a random number generator, a digital random number generator that will switch the value of the current source that you're using for the next cycle. So what you effectively end up with this system is that you end up hopping between different frequencies that are determined by these current sources, but your ramp is always maintained between the same exact magnitudes for the low side and the high side because of that ramp voltage detector. And because you always wait for the detector to determine the end of the ramp once it reaches that peak. So what's really happening is that you never allow hopping to happen except at exactly the end of every ramp cycle. And because you're keeping the same magnitude the same, and the switching duty cycle is actually determined by the intersection between the feedback voltage from the converter and all these triangles, from basic trigonometry, you can actually find out that the duty cycle, which is the ratio between the intersection and the base of the triangle, actually stays to be constant regardless of which frequency that you're using. So what this does, it preserves the same duty cycle as you change from one hopping frequency to another so that it does not cause any disturbance as in traditional frequency hopping. But what that also means, if you think about it, is that you're not really hopping every constant period of time. What's really happening that you're hopping every constant number of cycles of every frequency. So that's why we called it constant cycle frequency hopping as opposed to constant time frequency hopping. And because you're randomly changing the frequency, then you're effectively also randomly changing what? The hopping rate, because it's per cycle, it's not per period of time. So you have random hopping rate along with random frequency hopping. Okay, sounds good. So what does that mean though? Well, it means that when you go and analyze the spectrum, you really have to take into account the fact that you're not hopping at that constant rate, and you have to incorporate that within your analysis. And what that means at the end of the day, that the previous analysis that I showed you for frequency hopping becomes invalid. And if you really, why is it invalid? Because if you have a continuous clock like that, what you observe with the variable hopping rate, that every time you switch back to one frequency, then you actually keep accumulating phase shifts. You can compare the continuous clock with the actual signal, and you can see that every time you hop, you're accumulating a phase jump between the constant carrier and that actual switching signal that you're trying to analyze. So you have to take these phase shifts into account when you do your math to figure out what the spectrum really will be. And you can do some math and figure out what these phase shifts or phase chops, if you will, is going to look like mathematically. And then you can use some Fourier series math to try to figure out the impact of this. And what you realize is that these phase chops actually appear in the equation, that you can take them out of the Fourier series, and they will appear as if they are cosine and sine factors that modulate the DC component of that virtual gating sequence that we use to analyze the system. And that becomes very interesting because, we know that the reason we have a spur is because this gating sequence will always have a DC component because it's been between 1 and 0. But once you take the modulating terms into the account, which is multiplied by this, you're really converting the gating sequence in a bipolar sequence instead, because the cosine can be positive or negative, and also a variable magnitude. Once you look at it this way, you know what you need to do. If I want to get rid of the spur, let's make sure that the average of this signal is exactly equal to 0. And that will completely eliminate the spur. You didn't used to be able to do that in traditional frequency hopping because this thing inevitably is unipolar. You can never make the average of this thing equal to 0. It's always going to be half. But with that, you really have the ability to do this, okay? But how? What is the mathematical how do you ensure everything is random here? So how do you ensure that this happens? Well, mathematically, you can put it as an equation that what you're trying to do is to make sure that the sum of cosine of random phases is also equal to the sum of the sine of random phases. Both of them have to be exactly equal to 0. That's what that condition means. Well, but the problem that these phases are random. And, at the end of the day, if you actually take the sum of a cosine or a sine of a random phase, if you wait for infinity, it will eventually average out to 0 because the cosine and sine is symmetric. But I don't want to end up having to wait for a converter for infinite time to actually say that it's a Spur-Free. So the key is that how do you do that in a finite number of steps? Well, you can look a little bit at the math and you say, well, if I take that phase chop unit and make sure that it's a ratio between two integers, that actually results in an interesting scenario. It results that this condition now becomes a sum over a finite number of steps. That's what that condition means. It means that when you go around the circle, and instead of just scanning the whole circuit, you scan only specific points in the cosine circle, and if you strategically choose these points, you can choose them so that their average is exactly equal to 0. So let's try to do that. How do we solve this equation? This is the key to it. This is basically strategically trying to choose those phase chops to ensure that this sum, finite sum, is equal to 0. It took us a while to figure this out, and then until we came to know about some scientist, God bless his soul, he was living in Europe sometime, I think around World War II or something. His name is Dirichlet, and he came up with this Dirichlet kernel that basically tries, I don't know if you guys are familiar with that. We were not, so we had no clue about that kernel when we were doing that, but we found it in some math book. And it turns out he was trying to solve this problem. What is the sum of 1 plus 2 sigma from k to 1 to n of cosine kx, which looked exactly like the condition that we're trying to solve. And he figured out that it's a ratio between two sine signals like that. So we use our condition instead, and remember that you have to make sure that this is valid equal to 0 for cosine and sine. And we were worried because there is 90 degrees phase shift, so if you meet 0 for one, you're not going to meet for the other, so it may actually be impossible to do. But luckily, when you plot these things together, it turns out there are unique points that both of them are exactly equal to 0. And luckily also, these unique points are low sensitivity points, meaning what? If you don't meet it exactly, you move a little bit to the right or to the left, you still actually achieve almost full elimination. Okay, what does that mean for us in terms of the phase chops? Well, it turns out that the condition is a very trivial condition. We said before that the ratio between the two frequencies is an arbitrary integer to an arbitrary integer. Just make sure that this ratio is not equal to an integer. That's really what this whole thing is reduced to at the end of the day. And when you think about how we're implementing the ramp, we're implementing that using current sources. But isn't that exactly what you do in a segmented current mirror? It's always a ratio between fingers. So automatically it's ensured that it's a ratio between two integers. Just make sure that when you set that ratio, that you set it right so that it is not equal to an integer. And that basically turns out to be what the condition is. But this is only for two frequencies. If you notice there, that suggests that you can eliminate the Spurs with only two frequencies. But what if I would like to use multiple number of frequencies to improve my noise floor performance? Well, you can go through the math and all that stuff, and then it turns out that you only need to do the following. You only need to pick one frequency in the set of the multiple frequencies that you're using, and you don't have to make sure that every frequency meets that condition with every other frequency, because if you do that, it becomes virtually impossible to find a decent set of frequencies that will work. But what you only need to do is to make sure that the ratio between, you pick one frequency in the set, make sure that every other frequency can meet the condition with that particular one, and you're done. That's a sufficient condition to ensure spur elimination. So we go ahead and implement the system. We implement a converter. We use a mode where it's a traditional single switching frequency so that we use it for comparison. And then we did the option to have either 2 or 4 or 8. And we did that on purpose because we really wanted to try what happens with two frequencies, because eliminating the Spurs with only two frequencies sounded like too good to be true. So we wanted to test that, and we did our measurements, and here is what you get. So this is basically the top one is with a single switching frequency, so the traditional converter, and you can see the Spurs are very healthy, up to high frequencies. And then you enable our technique with 8 frequencies, and you can see what happened here, that all the Spurs are eliminated. Now, this here is only 5 dB per division. So if you look at the noise floor, it did not really affect that significantly, less than maybe less like about 2 dB increase or something due to spreading the energy of these Spurs. The fundamental, because it's the biggest one, so it's the largest energy, and you can see that you end up with a hump in the noise floor because you're spreading the energy of this one, of this fundamental across about 3.5 megahertz of bandwidth. And that's the absolutely minimum thing that you can achieve, because as opposed to sigma delta, you're not adding any extra noise in the system. You're just taking what you have and spreading that. So that's what that hump is all about. And you can see that it's confined to this area, meaning that it's not causing a broadband increase in the noise floor like in the sigma delta case. To make sure that we're truly eliminating the Spurs, and this is not just up to 60 megahertz, so we did the same measurement up to 60 megahertz just to demonstrate that the Spurs look really bad up to high frequency with the traditional design, but with our design, you're really eliminating all the Spurs everywhere. You pretty much have no Spurs in the spectrum whatsoever. Then we went ahead and we said, let's try it with 2 frequencies and 4 frequencies. And sure enough, your Spurs are actually eliminated as expected by the theory, but the peaking in the noise floor is higher, obviously, because you're distributing only using 2 frequencies, so the peaking in the noise floor will be higher. But what's interesting about that if you have a converter where peaking in the noise floor in this frequency range doesn't bother you, you can literally use very simple design with 2 frequencies to have a Spur-Free converter, no mixing, nothing like that. So it can be very effective, a cheap solution for this. One of the things that we also wanted to test is that, as opposed to the other techniques that they cause subharmonics to show up at low frequency, we wanted to make sure that we're not doing that and we're not disturbing the duty cycle. That's one of the things that we're doing, right? We're saying that we're not disturbing the duty cycle, which shows up as subharmonics. And we did the measurement for low frequency, 10 hertz to 5 megahertz, and you can clearly see that the fundamental Spur is completely eliminated as expected. But when you look at the random noise floor, you have a little bit of an increase here due to the peaking of the LC tank, but you literally have no subharmonics or no other harmonics. You have a pretty clean kind of spectrum even at low frequency. In the time domain, How does it look like? See, that's another thing that I like to emphasize, that in the time domain things can be misleading. But basically what you see in the top is the output of that converter. You can see all the parasitic inductance and everything is causing ringing and things like that. Well, you're talking about 48 millivolt or so of ripple that is showing up. And then once you enable our technique, you kind of see this thing. Now, we did that on purpose. And you could take a snapshot, like you freeze it in time, and all what you're going to see something that will look exactly like this. Just you will observe that the period is actually changing. But we left the scope free running and took a picture just to emphasize how random this thing is, that the scope cannot actually lock at any specific frequency, and that's why it looks smeared in like that. But what you notice is the following, or what we want to emphasize, that when you look at how much the ripple change, only from 48 to 52 millivolts, so you're literally not causing any increase in the magnitude, and there are no crazy glitches or anything weird is happening as you're actually hopping very fast. So that means you are not disturbing the operation of the converter by that hopping, as opposed to traditional frequency hopping. And the other thing I would like to emphasize, that of course when you look at the spectrum of these two signals, they look fundamentally different from each other. But when you look at it from a time domain point of view, you almost see no difference, right, in terms of magnitude. So it's another point to have in mind when you're dealing with noise. It's looking at it in the time domain is not really the right way to do that. So what is the impact on that power amplifier that I showed you initially? So let's look at that a little bit. And here is the experiment. You have your RF carrier, and we have three cases. The green cases, which you can hardly see, is with an ideal power supply, so just to have a reference point. The blue case is with the converter without our technique enabled, so single switching frequency, and you can see the spurs are pretty big here. And then the red one is once you flip the switch and enable the technique that we have, and you can see what happened. Those spurs completely disappeared because they do not exist anymore on the converter, and then you can see the hump in the noise floor, a little bit of an increase in the random noise floor, by you're essentially completely eliminating the spurs. You can do the same experiment with actual GSM data, and that becomes even more interesting, because when you look at the blue case, what does it mean to have these two big spurs? It actually means that they mix with the data, and you create two images of the data itself where basically these spurs. So essentially, if you don't have any spurs, you end up with the data here in the middle around the carrier. But because of the spurs, you create copies or images of the data. And that can also, not only that you're violating the spectral mask requirement, but that can be a security issue, because it means that if somebody got the image, he got your data, right? But when you enable what we've got, so this basically completely disappears, and then you are able to pass the spectral mask, no problem. One thing that I would like to emphasize here is that this hump in the noise floor, it is not a spread version of your data. That's a key thing. This hump in the noise floor is simply happening due to the randomness that you're using for your own switching. So if somebody got a hold of that, it looks like trash. It has absolutely nothing to do with the actual data that you're sending. So that can be important for people who worry about security and all that stuff. So in summary then, what we were able to achieve here is that with the constant cycle frequency hopping, is that we were able to do basically spur-free operation with minimum noise floor increase. So that's absolute minimum you can do. Minimal low frequency noise impact. You maintain time domain ripple magnitude, so you're not really changing that either. But one key factor is that you're able to achieve spur-free performance every node. So what does that mean? Because the spur-free operation here is not happening because you're filtering anything out. It's happening because you're fundamentally changing the switching behavior of the converter, meaning that every node in the converter will be meeting the same exact spur-free condition. So if you look at the switching node, if you look at the ground rail, if you look at the input, if you look at the substrate noise generated by the converter, they will all be spur-free kind of noise. And that can be helpful for integrating the converter or using it to power sensitive stuff or share its rails with other loads in the system. We were also able to demonstrate at a later paper that it works with both PWM and PFM control. Sometimes you actually have to use PFM control at light load conditions. And we were able to demonstrate that it works even in PFM control as well. So really, the whole technique can serve as more of something that can work at high load condition and light load condition. But one key thing that people seem to like about this is the fact that if you have an existing, because the whole design is really on how you generate the ramp signal to the converter, that means that if you have an existing converter that you like, you're happy with its efficiency, you're happy with its performance, all what you want is to get rid of the spurs. You don't have to redesign anything. You just take your ramp signal out, put this ramp signal generator in, you're done, you have a spur-free, you have your converter, but with a spur-free performance. So it's much easy to adopt this kind of technique into existing converters. You don't have to go and redesign your entire product line just to adopt this thing. Applications, direct powering of analog and RF, is a big thing. Polar power amplifiers, for example, like supply modulators for polar RF PAs can be very interested in that. Big improvement in EMI, electromagnetic interference, because now when you spread all that stuff, if you look at the rails, your ability to emit energy out of this becomes a lot less. So that's something that can be very helpful. So that was basically the technical portion. I would like to spend, I think we have a few more minutes that I would like to spend talking a little bit about power management and formal education. It's something that I personally am interested in terms of education. Well, the problem that we have with this, that there is really a big shortage in formally trained engineers in that area. The problem that if you look at the power electronics curriculum, it has nothing to do about VLSI or integrated circuit design, the stuff that we do in the IC industry. And if you look at the circuits curriculum, it has nothing to do about power. It's just that VDD that you draw in your circuit. So what ends up happening is that you interview people, even if you're trying to get PhD students or graduate students to work on the area, or if you're trying to hire somebody in the industry, very difficult to find anybody, at least a fresh graduate, with any idea about this topic. I personally did not study it in my undergrad or grad school. My PhD was high-speed transceivers, actually. It had nothing to do with power. So I learned that on the job when I was working at TI for a long time. So that's a big hole. And the problem with VLSI systems is that the power that you do for VLSI systems is really unique because it's custom power. You know your loads, so you have to worry. You have to really know analog and digital and process technology and SoC design. You have to know all these things to be able to design power for a VLSI system. So it requires a unique combination of background to be able to do that. So how do you answer that? How do you deal with this problem? Well, is the answer more research groups in the area? So let a lot of people like myself start creating research groups to work on the area. The answer is no, because at the end of the day, we focus on advanced topic. It's not really basic education, right? We go into deep stuff. It's limited number of students. How many PhD students are you going to have at the end of the day, and how many can you support? And how many can you produce? And so I think that's why it has to be resolved on the undergraduate level. It cannot be solved on the graduate level. You really have to make sure that your undergraduate students, when they graduate, they know what a power supply is. Because they don't. At this point, go get an undergraduate student in the circuits field after they're done with their degree and talk to them about power regulators or whatever. They know very little. So that's kind of a shame that this is actually the case. And in undergraduate, you have access to a large population. Now, the question is, as I mentioned, should we be injecting VLSI into power electronics curriculum? Or should we inject power electronics into VLSI curriculum? So that's a question that you have to ask. And my experience has been, forget it, you're not going to be able to inject VLSI in power electronics curriculum. They have so much stuff there that is missing from the VLSI side. Very difficult to get somebody in the power electronics and try to teach him, analog and RF and IC design. There is just too much to worry about. On the other hand, if you get an analog and mixed signal guy, for example, and you try to teach him linear regulator, he already knows that. This is just an amplifier, right? So very easy to teach them that. Very easy to teach them switching power regulators or battery chargers. So the basic concepts for power are very simple. The circuits people can learn it very quickly. So that's a much more effective way to do it. But then the question, where do you do it? Should I create a new course that's dedicated in power on the undergraduate level? Not practical either. If you look at the circuits curriculum that we have, it's already very crowded. But what I like to do is to try to leverage existing VLSI curriculum so that you inject concept of power within them. Now, this is sequence, of course, that we use at Iowa State, but UW and many other schools will have kind of the same concepts. But if you look at the most basic circuits course, where we teach people RLC, circuits and mesh analysis and circuit analysis and all that, if you spend one lecture just talking to them about that the inductor and the capacitor are energy storage elements, and maybe add a switch there, and you can very easily explain to them the concept of a switching power supply by spending just one lecture talking about the fact that you can use inductors and capacitors to actually create a power supply. So that's an easy thing, very low overhead effort on your part as a professor that will bring a lot of attention to this topic to students. Once you go to the system design level of electronics, we use courses that we use an op-amp and okay, let's build an oscillator, let's use the op-amp as an amplifier and so forth. You can simply just add one example to use the op-amp as a linear regulator. Very low overhead again, and then you bring to the attention of the students that there is something called power supply design, and it is not just a given thing that you have in the system. Then as you move to transistor level design, you don't necessarily have to teach them transistor level design of power converters, but whatever it is that you're teaching them, an amplifier design or a digital circuit design, you just basically work with them to check out the performance if VDD changes. What if it went up a little bit? What if it went down a little bit? By doing that, they start actually understanding that that level of the power supply is very critical to their performance. And it does change the performance of their circuitry. And it is a good idea to bring to their attention that power supply is important. You cannot have it for granted. I'll tell you that one of the tough lessons that I learned at TI when I started working fresh. So I'm going there, and it's VDD, right? So I go and design my circuit, and it works beautifully. And then my boss at the time comes to me and say, I was using a 3.3 volt supply. And then, he just says, oh, yeah, did you try it at 3.0 and 3.6? I was like, why? Why? Isn't the power supply 3.3? And he looks at me and say, yeah, but it has some tolerance to it. It can be as low as 3.0 and as big as 3.6. So I was thinking, that should not be a problem. And I go to my simulator, change the power supply. And man, the circuit crashes at 3.0. And it was a testament of how bad my design was, that it was, really bad, that it works at 3.3, you go down to 3.0, and the thing doesn't meet the speed anymore. But then, all of a sudden, I realized, actually, that power supply can change. Many students will graduate without, if it happens to them, it makes sense, but, initially, they wouldn't. So you can at least bring the students to see that this is an important thing. And linear amplifier design and compensation, towards the end, you're talking about Miller compensation and all these things. You use it as an LDO. It's very simple, really, to do. And as I said, very low overhead. So I believe that these can be small changes in the circuits curriculum that can lead to a big impact. And one of the things that I did at Iowa State when I first joined was exactly trying to do that I created. That was a graduate level course, actually, not an undergraduate level course, but it's a course that is called Power Management for VLSI Systems. So it's basically teaching all kinds of different power management on the system and circuit level, but from a VLSI perspective, not from the traditional power electronics perspective. And that's something that is certainly was very popular course when we initially started that. Well, thank you very much for your time. I'll be happy to take any questions if you have any. Yes?
So you showed those lovely figures about the suppression of the Spurs, and that looked like it was under a fixed load. Could you say a little bit about what happens if the load varies? Or is that same general?
Yes. So the question is, this is under, the results that we're showing is under a specific load condition, and the question is, what happens if that load varies? And actually, the answer to that question, that it's independent of the load. If you look at the elimination condition, it's actually inherent to the switching behavior of the converter itself. In fact, if you're using PWM control, that switching frequency is constant, so you determine that, and the duty cycle does not even change that much with the load current. It will change a little bit to compensate for losses, but it basically has no effect whatsoever in your ability to suppress that Spurs. So it is not a function of the load current And even if you use PFM control, which is another paper that I'm not covering in this presentation for the sake of time, but we were also able to demonstrate that you can use the same technique, even if you don't have control over the switching frequency. One thing that can come to mind is that, well, I am controlling the frequency in PWM control, so I can choose the frequencies however I want, right? So I can make them to meet the condition. But if you look at a PFM control, where you're actually controlling the pulse width and letting the switching frequency vary with your load, and your question would be relevant there, then how do I ensure that these frequencies meet that condition? They're determined by the load at the end of the day. But what we were able to demonstrate is that if you find a parameter in the converter that is indirectly related to the switching frequency, even if it's non-linearly, if you set that parameter to meet the condition, meaning the ratio between integers that is not an integer, your frequencies automatically meet the condition. So in that other paper, we implemented a constant on-time controller. So we have a constant pulse width, and we hop the pulse width, not the frequency, the pulse width, so that we meet that condition. Our frequencies follow and also meet the condition, and you end up with a Spur-Free kind of behavior. I actually have the slides, but that I can show you maybe after we're done. Yeah, thank you. Did that answer your question? Yes. Yes.
When you suppress the Spurs, you are using an extra circuits to do that.
Yes.
So wouldn't that extra circuit consume a little bit of energy?
Yeah, that's a very good question. But here is the answer. The short answer is no, and the reason is the following. Interestingly enough. Okay, so here is why. Because what you observe in these current sources that we have is that when we're using one of them, all of the others are actually turned off. So you're not consuming anything during that time. And sometimes, so let's say the single switching frequency case, let's say it uses that middle current source, right? So what we're doing now is that instead of using that single, we're using sometime higher current and sometime less current. When you look at the statistical average, the total current is always equal to the single switching frequency case. In fact, when you compare the efficiency of this with the single switching frequency case, you should see no degradation in efficiency. Because on average, what happens is even your switching losses are a little higher here, but they are a little less here. If you adjust the frequencies so that they are evenly distributed around the single switching frequency case, you see no degradation in terms of the efficiency. But to demonstrate that even if you don't, things are not so bad, we did our experiments where we chose all the frequencies in our technique to actually be higher than the single switching frequency case. Why? Because we wanted to show exactly that. Even if you do that, our degradation efficiency was less than 1.7%. So even if you make these frequencies not evenly distributed, impact on efficiency is not that significant, because when you look at it, it's all digital implementation if you think about it. These are all just random number generators. They consume very little current. So in terms of efficiency, it's not really impacting. Yeah.
Well, let's thank our speaker.